Welcome, curious minds and aspiring scientists, to the Simple Science Summary. Ever wondered why some chemical reactions, just happen instantly, like that fizz when you drop a tablet in water, while others, like iron rusting, seem to take forever? Or why even a reaction that gets really hot still needs a little nudge to start? Well, today we're diving into the energy secrets behind chemical changes. We want to give you a really clear picture of energy and change.
Exactly. And if you're a grade 12 student here in South Africa getting ready for your national senior certificate examination, this is for you. We're looking right at your physical sciences curriculum, specifically what's in the CFPS document and the examination guidelines. Our goal here is simple: cut through the complex stuff and give you the key ideas, not just to pass your exams, but to really get how things work.
Absolutely. Forget feeling swamped by textbook definitions. Think of this as your shortcut. We'll unpack the basics of energy changes, why some reactions feel hot, some cold, what it really takes to kickstart a reaction, and how we can actually speed them up. And we'll stick to the concepts. No getting lost in complicated formulas or symbols. Just what you need. Ready to jump in.
Let's do it. So first things first, a really core idea in chemistry and physics is that energy is always involved when stuff changes, chemically or physically. It doesn't just appear or disappear. It gets, exchanged or transformed. And the study of all this energy interaction with matter, that's called thermodynamics.
Okay, thermodynamics. And in chemical reactions specifically, we hear terms like heat of reaction or enthalpy change. What's that telling us?
Good question. That heat of reaction, often shown as delta H, it's basically the net energy change during the reaction. It's the difference between the energy the products end up with and the energy the reactant started with. It tells you if energy went in or came out, overall.
The bottom line on energy flow.
Yeah.
And that leads us to the two main types, right? Exothermic and endothermic. Let's start with exothermic. What's happening there? Like at the molecule level, that makes things heat up.
Right. Exothermic reactions are the ones that release energy into their surroundings. You touch the test tube, it feels hot. That heat, that's the energy being released. What's happening is more energy gets released when the new bonds form in the products than the energy that was needed to break the old bonds in the reactants. And that extra energy comes out as heat, so the temperature goes up.
Ah, okay. So the heat we feel is literally energy being pushed out. How do we show that? Is there like a code for energy leaving?
Yes, exactly. There's a sign convention, which is really important for your calculations later. For exothermic reactions, the enthalpy change, delta H, is negative. We write delta H 0. That negative sign doesn't mean less than nothing. It means energy is leaving the system, exiting.
Exiting. Negative. Got it. Like burning a candle, lots of heat and light coming off. Or a car engine burning fuel. Definitely feels hot. Even rust, you said, it's slow, but still releasing energy.
Yep, even slow processes like rusting are exothermic, just releasing energy over a much longer time. So if exothermic reactions release energy, endothermic ones must do the opposite, right? What does that mean for how they feel?
Okay, so if exothermic give off heat, make things hot, endothermic must pull heat in, make things feel cold.
Exactly right. Endothermic reactions absorb energy from their surroundings. So the reaction mixture usually feels cold. It's literally sucking heat energy in from whatever's around it to make the reaction happen. In this case, it takes more energy to break the old bonds in the reactants than the energy you get back when the new bonds form in the products. So there's an energy deficit, and it has to be made up by pulling energy from the surroundings, which cools things down.
Like those instant cold packs. You snap the thing inside, mix the chemicals, and boom, it gets freezing cold. That's ammonium nitrate dissolving, right? Pulling in heat.
That's a perfect example.
And photosynthesis. Plants absorbing sunlight energy to make sugars. That's a huge endothermic process.
Absolutely vital one. And again, there's a sign convention. For endothermic reactions, delta H is positive, delta H 0. The positive sign shows energy is being added to the system, absorbed.
Okay, positive for energy in, negative for energy out. But why? What's the fundamental reason energy is released or absorbed? Is it really all about the bonds?
It absolutely boils down to the bonds. This is key. Think about it like this. You always need energy to break bonds. Always. It takes effort to pull things apart. But when new bonds form, energy is always released. Things settle into a more stable state. The overall change, that delta H, just depends on the balance. Was more energy needed to break bonds or was more released when new ones formed? That's the whole story.
And this ties back to that fundamental rule, the law of conservation of energy. Energy isn't just vanishing or appearing.
Spot on. Energy is conserved. It just changes form or location. In an exothermic reaction, the chemicals lose potential energy, and that energy warms up the surroundings. Total energy stays the same. In an endothermic reaction, the chemicals gain potential energy by taking it from the surroundings, making them colder. Again, total energy is conserved, it just moved.
That makes total sense. Okay, so often in our textbooks, we see these drawn out as potential energy diagrams. How do those graphs help us see what's going on?
They're super helpful visuals. Imagine a graph. Energy goes up the vertical axis, and the reaction progress goes along the horizontal. For an exothermic reaction, you start on the left with reactants at a certain energy level, and you end on the right with products at a lower energy level. There's a visible drop, shows energy was released.
Like rolling downhill energetically.
Yeah.
And endothermic would be the opposite, going uphill.
Precisely. For endothermic, the reactants start lower and the products end up higher in energy. You see that climb on the graph showing energy had to be put in. These diagrams map out the energy journey of the reaction. Very useful.
Right. Now, something interesting, even if a reaction is exothermic, so it wants to release energy like that downhill roll, it often needs a push first, like getting a ball over a little hump before it rolls down the big hill. That push is activation energy. Why? Why the initial speed bump? Why can't they just go?
That's a really important question. It gets to the heart of reaction mechanisms. Activation energy is the minimum kinetic energy that reactant particles need when they collide for that collision to actually work, to transform them into products. And why is it needed? Because before you can make new bonds, you have to break the old ones first. And breaking bonds always costs energy. Activation energy is that initial investment to start the bond breaking.
Okay, so it's the entry fee to start breaking bonds. And at the very top of that energy hill, that peak on the diagram, there's the activated complex. What's that?
Oh, the activated complex. It's a very temporary, unstable, high-energy arrangement of atoms that forms right at the peak of the energy barrier, just as reactants are turning into products. It's not quite reactants, not yet products, a really short-lived intermediate state.
This idea of needing enough energy makes me think of those Maxwell-Boltzmann distribution curves, the ones showing particle energies.
Yeah.
How does that connect?
Oh, that's a perfect connection to make. It's crucial for understanding reaction rates. See, at any temperature, particles in a sample don't all have the same energy. Some are slow, some are fast, most are average. The Maxwell-Boltzmann curve shows this distribution. And the key thing is, only the particles with kinetic energy equal to or greater than the activation energy can actually react when they collide. Only a fraction of them have enough energy.
So if we heat things up, increase the temperature, we're giving more particles enough energy to make it over that activation energy hurdle.
Yeah.
Is that why cooking is faster at higher temps? More molecules have the energy to react?
Exactly. You raise the temperature, the whole curve shifts. More particles, a larger proportion, now have enough energy to overcome that barrier. So you get more effective collisions per second, and the reaction goes faster. It's why we heat things up to cook, or why industrial processes are often run at high temperatures to be efficient.
Okay, so thinking about needing that initial push, are some reactions kind of ready to go once they get that activation energy push, while others need, like, constant energy just to keep going? What's this spontaneous versus non-spontaneous idea?
Yeah, that's a good distinction the guidelines sometimes mention. Basically, spontaneous reactions, once you give them that activation energy, they'll proceed on their own. They naturally tend towards products. Think combustion. Non-spontaneous reactions need a continuous supply of energy from outside to keep going, like photosynthesis, take away the sunlight, the energy source, and it stops.
Right. Okay, so we know about the energy changes, the activation energy hurdle. What if we want reactions to go faster, but without just cranking up the heat? That's where catalysts come in, right? The reaction speed up artists. What exactly is a catalyst?
Yes, catalysts. They're fascinating. A catalyst is a substance that speeds up a chemical reaction. But, and this is key, it isn't used up or permanently changed itself in the process. It helps out, then it's regenerated. And how does it speed things up? By providing a completely different reaction pathway, an alternative route. And this alternative route has a lower activation energy.
Ah, so it's not about pushing harder over the same mountain peak. It's like finding an easier trail, or even a tunnel.
That's a great analogy. A tunnel through the mountain is perfect. They might do this by, say, helping the reactant molecules line up correctly for collision, or by reacting temporarily to form an intermediate compound that then easily forms the final product. The amazing thing is, this allows reactions to happen quickly at much lower temperatures than they otherwise would, saves huge amounts of energy, makes processes viable.
And crucially, they don't change the start or end points. The overall energy change, delta H, stays the same.
Absolutely critical point. You'll definitely see this tested. A catalyst lowers the activation energy pick on the diagram, but the energy of the reactants at the start and the energy of the products at the end. unchanged. So delta H, the overall energy difference, is exactly the same with or without the catalyst. It just makes the journey from start to finish much faster and easier.
Wow. And the applications are huge, like in cars. Catalytic converters, they use catalysts, don't they?
Oh, massively important application. Catalytic converters use catalysts, often precious metals like platinum or rhodium, to convert harmful exhaust gases like carbon dioxide, nitrogen oxides, unburnt fuel into less harmful things like CO2, nitrogen, and water. It's a huge deal for reducing air pollution from vehicles.
And it's not just cars and factories. Our own bodies rely on catalysts constantly.
You mean enzymes? Yes, enzymes are our biological catalysts, usually proteins. They are essential for, well, pretty much every chemical reaction in our bodies: digestion, metabolism, building tissues. Without enzymes, these reactions would be far too slow at body temperature to keep us alive, and they're often incredibly specific, one enzyme for one particular job.
It's amazing. These chemical principles are literally running everything. Are there any, common mistakes people make about catalysts or downsides?
Good points. A common mistake is thinking they get used up. They don't, they regenerate. As for downsides, in industry, catalysts can sometimes get poisoned by impurities in the reactants, which stops them working. So maintaining catalyst activity can be a challenge, and sometimes they're very expensive materials.
Okay, so let's recap quickly. We've looked at energy changes. Exothermic releasing energy, feeling hot, negative delta H, and endothermic absorbing energy, feeling cold, positive delta H. All down to bond breaking and making.
Right, and we saw that activation energy is that initial hurdle, the energy needed to get bonds breaking.
Which explains why temperature affects reaction rates. So much more particles have enough energy.
And finally, catalysts. The clever substances that find an easier, lower energy pathway to speed things up without changing the overall energy difference.
Lowering that activation energy peak, it really does connect so many ideas.
It really does. And once you start looking, you see these principles everywhere.
Absolutely. Just think about the air you breathe, the food cooking on the stove, maybe a battery powering your phone. It's all governed by these ideas of energy and change we talked about today. How many other examples can you spot? Where energy is being released or absorbed, where maybe there's a hidden catalyst making things happen efficiently. The more you look, the more connections you'll find between the chemistry you're learning and the amazing world around you. Keep exploring, keep asking questions, and keep learning.